Welcome everyone to this Tuesday's lead theory. So we're trying to wrap up what we did last time with some special classes of the algebras, and so in order to do that, we need to introduce the upper central series and the lower central series. Let G, mathfrak G, is a Lie algebra. So that was this vector space that had these brackets that was skew symmetric and who had this Jacobi identity. So then its upper central series is defined as follows. G0 is just G, and then we get iterative versions of G by applying the Lie bracket again and again. So this is the upper central series, and the lower central series is defined as in a similar way. Let's say lower than the indices go low. We start off with G, and then the only difference is that here we are not inserting the whole Lie algebra at each point. We are inserting just the previous thing that we got from the bracket inside.
Remember to keep those indices down.
Yes, that's a good point. So here we are, we should take them down. Thank you very much, Hannah. So that means that Mark in particular, G1 up is the same as G1 down. That's just bracket of G with G. And that is an ideal in G. And then in general, the lower J is inside of the J upstairs. Because here we're doing the entire Lie bracket, whereas here we're just doing this thing here. So the lower central series will sort of vanish faster if than the upper central series. And then definition, we say that G is nilpotent if G upper J is equal to 0 for some J, and we say that G is solvable if the lower G is equal to 0 for some J. So let's do some examples for these. So the first example is G is equal to SL to R. So we saw last time that SL to R, which was two by two matrices, real matrices with trace 0, that this was simple. And hence, since G1, G bracket GG is an ideal, we have that in this case, G0 is equal to G0 is equal to G1 is equal to, yeah, GJ downstairs is just SL to R. So no matter what we do with SL2, if we take all the brackets, we'll never get anything less. This will be the same for all the algebras. So next example, we can take the Heisenberg algebra. Let's write it as H1R for all, for all simple algebras. Press here, okay. That's it. And then the Heisenberg algebra is a collection of all 3 by 3 matrices like this, where A, B, and C are real. So they are hence matrix 3 by 3 matrices that are 0 everywhere except on top of the diagonal. And if we then take the product, or sorry, the bracket of two such matrices, A A1, B1, C1, 0, 0, 0, A2, C2, B2, 0, 0, 0, and then take the bracket, what we're left with is something that's 0, except here, where it's A1, B2 minus B2, A1. So if we take these upper triangular matrix, we are left with something that is only upper triangular so it only has a non-zero index in the corner. And notice that the C's didn't do anything when we did this bracket, right? So the C's did not contribute at all. So that means that G1, which is then which is also G lower 1, G bracket G, will be all matrices like this. Where R, C, S in R. So these are the only ones that are in G1. And then if we take a bracket with a matrix 0, 0, A, 0, 0, B, let's see, 0, C, with some other matrix 0, 0, 0, 0, 0, 0, C2, 0, 0. If we compute the Lie bracket, this will be the 0 matrix. Hence, G2 will just be 0. And this will also be, sorry, G upper 2 will be 0. This will also be lower 2, which will then be just G1 bracket with G1. So hence, let's see, I should have written this as G. Hence, G equal to the first Heisenberg algebra is nilpotent. So here, if we take, so another way to interpret nilpotent is that if you take enough Lie brackets, then you will always end up in 0. So if G of S is equal to 0, then the brackets x1, x2, xs, sorry, s minus 1. Let's see, no, this is fine. For G1, it's 2 brackets, so this should be S, and then S plus 1. And then all of these closed, this will be equal to 0. So this is a way of thinking about nilpotent, is that if you apply this bracket enough times, then no matter which element you put into this bracket, you will get 0. So this Lie algebra is hence solvable, and solvable is then a special case. So solvable will then it's nilpotent, and nilpotent will also be solvable. However, things that are solvable don't need to be nilpotent. So to see this, let's do another example. Let me go back to my black. So C, consider the algebra. Let's call it F to R equal to G, where G is the set of A and B, 0, 0, 0, where A and B are real matrices. So this can then also be seen as the span of X and Y, matrices X and Y, if we let X be 1, 0, 0, 0, and Y equal to 0, 0, 1, 0. So in other words, it's a two-dimensional Lie algebra. And for those of you who've done the exercise on this, you know that there are not that many options when it comes to two-dimensional Lie algebras. So if we take the brackets of these two matrices, compute them, y is xy minus yx. The result is that we get y. And that means that hence for upper central series, G0 is then G. G1 is the bracket of G and G, which is then the output here, which is the span of Y. That's everything we can get in the output. However, if we do now G2, that's that will then be G times G1. Well, here we have Y, and here we have X. So again, we get the span of Y. And this is true for G3, G4, and so forward. Sorry, I'm getting a call. So this one will not be nilpotent. Because we'll never get anything lower than Y. And the reason is that I can do X, 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 as many X's as I want, and it's still equal to Y, right? So, but it is solvable because if I take the lower central series, then G1 is again G bracket G, which is a span of Y. And then G2 is then G1 bracket with G1. So this is just a one-dimensional thing bracketed with itself, and this is skew symmetric, so this is 0. So we have that. This is solvable. Are there any questions related to this? Okay. So these are the examples for. So we have these three things. We have simple, we have nilpotent, and we have solvable. Now, why are we learning about this? Well, it turns out that later when we're going to work with the representation theory, representations of each of these cases will be very different, right? And there will be some cases where we can use some techniques and some cases other. And this is why we're introducing this now, because it will be useful later. But we'll still have to finish the chapters on Lie algebras before we get to the actual applications. Now to connecting, that finishes up the things we were supposed to do last time. Now to connect this with what we had before. So let's talk about the Lie algebra of matrix Lie group. So there are actually several ways you can obtain this thing here. So we'll see that the way you can obtain the Lie algebra is simply by taking a curve in your matrix group, and then that's the identity at 0, and then just differentiating it and see what kind of derivatives you can get. But we're a little bit away from that. So we're going to get to this result in this description eventually, but we're going to have to go to some other formalism first. So that's why we have this rather particular definition of what a Lie algebra is. So for a matrix Lie group, G inside of G, L, and K, let math frac G be the collection of all X in G, L, and K such that E, T, X is in G for any T in R. Then G is called the Lie algebra of G. So in other words, if you exponentiate with T with Tx, then you end up in your Lie group. That is what we call the Lie algebra. Note so it's sufficient that E of t of x is in G for small t, so t less than some epsilon. Since we can use the property t of x times E of Sx is equal to E t plus S of x, right? So if we have that this exponential map is contained inside the group for very small t, then we can just multiply them enough times to get any large t that we want, right? So it's enough that this starts out in T and G, and then it will never leave. But it's not sufficient that e to the power tx is in G. So if we take, for example, a theta equal to 0 minus theta, theta 0. No, sorry, that the exponential of x is in G. So that's not enough. That it's just exponentiating in the matrix, you end up in G, that doesn't tell you anything. So the example is if I have this matrix here, then e to the power a theta will be cosine theta minus sine theta, sine theta, cosine theta. So in particular, E of A of 2 pi, it's just the identity matrix, right? So it means that E to the power 2 pi will be in any Lie group, any matrix Lie group. That does not mean that E to 2 pi is in the Lie algebra, because we need it to hold for any t in between. So for any matrix group, but a to pi is not in any Lie algebra. Not necessarily in the Lie algebra. So the next thing we need to do in order for this to make sense as our Lie algebra definition is that we need to show that it's an actual Lie algebra, right? So here I just took a collection of things where the exponential map goes into. So I didn't say that it's a vector space. I didn't say that there's a bracket. I didn't say anything, right? So, so that's the first thing we need to prove is the following lemma that what we've said is the Lie algebra of G of the matrix group G is in fact Lie algebra. So that is G is a vector space. And G is closed under the commutator bracket. And then furthermore, if A is in G and X is in the Lie algebra, then what we will call add A apply to X, which is A times X times A inverse will also be in the Lie algebra. So perhaps I should write this out. Is also in G. So we have this property. It will actually be a Lie algebra, and it will be closed under conjugation by elements in G. So for the proof, so what do we need first for a vector space? We need scalar multiplication. And then for this, we have that if X is in G, then Sx is in G. Since e to the t s x is equal to just e t s x, which is in G by assumption. For 2, so then we have addition. And then we need to use this identity that we've used several times in related to relating plus and the exponential map, which is that if you have e of x plus y, this is equal to the limit of m going to infinity of e of x divided by m times e of y divided by m, and then you take that to the mth power. So if x and y are in G, then am equal to e of t of x divided by m times e of t of y by m to the power m is in G. For any t, because because the x was in the Lie algebra, so all of these should be in the group, and all of these should be in the group, and this should be closed by multiplication. And I should be able to multiply them as many times as I want. And then since G is closed, here we're going to use this again, closeness assumption. Some of you wondered why in the beginning why we'd have it. Then a infinity, which is then the lim of m going to infinity of am, which is lim m going to infinity e to the t tx divided by m e ty divided by m to the power m. This will then be equal to e to the tx plus y, which will then be in G. Right? Because the limit here, because this is closed on the limits, so if we take the limits of all of these a's, which has limits e to the tx y, this has to also be in G. And then hence it follows that x plus y is in G, is in mathfrak G. So it's also in the Lie algebra. And in this sense, we have now the two components that we need in order to have a matrix Lie group. Now, in order to have a vector space, sorry about that. And then for the next one, we'll actually need this adjoint part first. So let me do that. So if I'm taking e of t add x, now add a x, then this should be equal to that's e of t. That's e a of tx, a inverse. And then we had earlier properties of the exponential map that if we have this kind of conjugation, we can just move it outside. And so we get that this is e of tx times a inverse of G, which is in G when x is in the Lie algebra. Right? Because that means that if x is in the Lie algebra, that means that this is in G, and this, by assumption, is in G already, and it's close on the multiplication, so it ends up there. And then the final touch, here, what we need for the final part is that we need that the exponential map at 0 has derivative x. So we need the following results from before, that the derivative of 0 is x, and that we have a product rule. So if we have a of t times b of t multiplied, then this is just the first one multiplied with the second one. No, sorry. That's not how product rules work. Plus a of t ddt b of t. And to see this, you can just use basically what are the coefficients in the product matrix for a times b? Well, they're given by a sum of products of elements, and that gives us this result right here. Okay, and if we then use this thing here, then if X and Y are in G, then add e to the t x. Y is also in, that is e t x y, e minus t x will then also be in G. And then that means that e of tx y of minus tx here, if I then, since I have the plus, I can also I also have a minus, so I can subtract. This will be in G. And if I'm closed under scalar multiplication, so I can also divide by t. And then since finite dimensional vector spaces are closed, then the limit here, as t goes to 0, of 1 over t e to the tx y, e minus tx minus y, which is equal to actually the derivative of e tx y, e minus tx yx when t is equal to 0. And then I'm applying this product rule again, and I'm getting that this will be d dt etx at t equal to 0 times y plus y times d dt e to minus tx t equal to 0. And this will be then x y plus y minus x, which is the bracket of x and y, which then is in G since this original limit was in G. So that's sort of the detour that we have to make in order to get also our Lie bracket into the algebra. Bring in, so now that we've established that we actually have, let's go back to the theorem. So we actually have a Lie algebra associated to a a label associated to each matrix Lie group. We can look at what this is in the individual cases, and we finally now have an idea of what a complex Lie algebra is. So definition, matrix G, the matrix group, Lie group G. G is called complex if its Lie algebra G is closed under multiplication by I. And what we'll see now is that a lot of the Lie groups that we define using complex matrices and can only be stated using complex matrices, they are not complex. So they do not have complex algebras. So let's start with what are the Lie algebra of the different Lie groups that we've seen so far. So the Lie algebra of GL and K is then, of course, called small g and k, and it will consist of all m times n matrices. So all matrices are in the Lie algebra of the general linear group. For the special linear group of SL SLN K, we have then the algebra that we've already seen, which is small SLN K, which is the Lie algebra of all matrices with trace 0. So in other words, so recall that the special linear group, that was all the matrices with determinant 1, and that corresponds to the Lie algebra of having trace 0. And in particular, SL and C is a complex Lie group. So having trace, if you have a matrix with trace 0, then multiplying by I still gives you trace 0. So that doesn't change anything of the trace. Let's write that out since the trace, unlike the determinant, is linear. Then for the unitary group, let's do a curl here, is then small un And that will consist of all matrices, all complex matrices, with X star being equal to minus X. So that gives us a Lie algebra. So then, and I can write that in blue, in particular, UN is not a complex Lie group. Since if X star is equal to minus X, then IX star will be then just taking the conjugating Y and then X star, but this will be minus I, and then here I will have minus X, and now I'm getting back to IX. So you see here that if I have a matrix that's non-zero, which satisfy this, that it's sort of skew adjoint, that the conjugate transpose is equal to minus, then we have, then multiplying by I does not give us a matrix that's like this. So UN is not a complex Lie group, even though it only consists of complex matrices. And okay, and we're going to get into the separation a bit about real and complex later and talk about complexifications. But basically, a way to think about this is that if you have a complex Lie group, you can actually talk about things being holomorphic and other stuff that you learn about in complex analysis, and you can't do it if you don't have a complex Lie group in essence. If we go the orthogonal matrix, then the orthogonal group and the special orthogonal group both have Lie algebra, which we'll write as small SON. See if I'll make them a bit more edgy, like this, small SON, which is then the analog of what we saw here with the unitary group, where instead of the conjugate transpose, it's just a normal transpose, since we're just dealing with real matrices. And of course, if your Lie algebra only consists of real matrices, then of course you are not a complex complex Lie group, because if you multiply by I, you get something that you didn't have before, because now you get complex numbers, right? So you get out of your Lie algebra. So I'll prove this. Are there any questions to the statement itself?
Sorry, would it work if the field is complex numbers?
What equal what? Sorry, I didn't get the kind. What happens if the field is complex?
When you're getting them, the elements of small s or n.
Yeah.
GLNR.
Yeah.
Can it work if the field is complex numbers?
So if you, yeah, this is a good question. So let's put it like this. So it does actually work. So you could, yeah. So remark. So we can define O and C, which are then all matrices A with A transposed being equal to the identity, but with complex numbers, right? So this we can do. So this will not preserve any inner product or anything, but it's fine. It will be a Lie group, and with the algebra, let's say O and C, because now it will be different for ON and SON. Which is GL and C, and this, yeah, will have the same. And this will be closed. By I. So simply put, the problem here is that we get this conjugation of the I, which breaks this thing, breaks the skew symmetry. Like if you don't have the conjugation, this is not a problem, right? So IX trace is just, or IX normal transpose is just I times that transpose. So we don't have any problems with before. So O and C is complex Lie. Yeah, so when I'm doing these lectures, I don't have time to do absolutely all of the groups that are in the book. So one of these ONC, this complex orthogonal matrix is one that I skipped. I also skipped the orthogonal groups where you have a non-positive definite metric. So when you have a Lorentzian metric, for example, there's a special orthogonal group for these kinds of things. Yeah, I also skipped the symplectic group and stuff like that. But these are interesting examples. It's just that I can't do everything during these lectures. So what about the proof of this? So for A, what was A? So for G, L, and C, then we have that ETX is in GLN, or not C, but K for general K. Then we have that this matrix exponential is in this group for any X in GL and or the matrices by definition. right? So the exponential is always an invertible matrix. So if you take any matrix and exponentiate it, you end up in the general linear group. So this is just by definition, and then it can't get any bigger than all of the matrices. So that's it. So for B, that's SLN to KR, then for X in M and K, we have that the determinant of ETK, what was that? We had a result earlier that says that the determinant, if we took the determinant of an exponential, that was equal to the trace of T of the matrix itself, which was equal to T of this thing here. Hence, that ETX equal to 1 for all T is equivalent to the trace of X being 0, right? You need to have, yeah. So the logarithm of 1 is 0, so you need to have trace 0 all the time up here. So for C, if for the unitary matrix, so the unitary matrix are, remember, are matrices such that U conjugate transpose should be equal to U inverse, right? So that means that if X X star is equal to minus X, then E to the X T star is equal to E T X star. That was one of the associated things about the exponential map, was that it was, we have a conjugate transpose, we can always just do that with the matrix inside. Now R is real, so this is just T X star, and now this will then be T E times X minus, which is E minus TX, which is ETX inverse. So hence ET of X is in UN. Conversely, if ETX is in UN, then then E T X star times E T X should be the identity. No, let's not do it like this. Yeah, should be equal to E Tx inverse, or E of minus Tx, but it should also be equal to E of T of X star. And hence X star is equal to minus X. Because any group homomorphism from R to G could be uniquely represented as T maps to E T Y for some Y. So if you have these sort of these sort of groups going into G, which both of these are, then they have to, if these two things equal for all time, and so if this thing and this thing equals for all time, then they have to be the same element because of this unique representations of semigroups. Then the proof for n is the same. It's the same as for you, and it's just replacing it's just making all the matrices real, right? Furthermore, since that of A is plus or minus 1 for A in ON, it follows that the determinant of E to the Tx is the determinant of E to 0 times x is 1 from the continuity of the exponential map. Of the determinant and exponential map. So it cannot skip from +1 to -1. So it has to be 1 all the time. Hence, if X is in the Lie algebra of ON, it will also be in the Lie algebra for SO. So we don't get any sort of difference because okay, the Lie algebra is all things that stay inside the group after you use the exponential map, and all of these things that stay inside the group that use the exponential map, they will stay. You only get things with determinant 1, not with determinant -1. So again, you want to consider the orthogonal matrix as being like two different globes, one globe with positive determinant and one globe with negative determinant, and these two never meet in any way, and all the exponential map, they go into the positive parts. Let's see. Yeah, let's talk a little bit about finally about morphisms of Lie groups and Lie algebras, because this will actually be a key step in our transition from going from working with Lie groups to just working with Lie algebras, and a way to show a lot of nice properties. For example, we've only assumed so far that, like, for example, group homomorphisms are continuous, and in fact, we're going to show that if they're continuous and the group homomorphisms, they will actually be smooth. So the theorem that we're going to show is that if we have a group homomorphism, let's say Lie group homomorphism, then there exists Lie algebra homomorphism small phi going from the Lie algebra of G to the Lie algebra of H, such that if I take something that's in the Lie algebra of G and apply this phi, then it's equal to E of the small phi of X. Yeah, okay. Where X is in G. So any any Lie algebra homomorphism gives us Lie group homomorphism, and then we have some other properties. So if we apply this add map again that we had before, remember this was just conjugation by that by a matrix, then this phi is invariant under this A map, add map. This is the same as first applying large phi to A, and then applying X. And then finally, how do we get this Lie algebra homomorphism? Well, we can take look at the exponential, look at what it is after we apply the mapping phi, take the derivative, and then the output will be the results of this group, Lie algebra homomorphism. Now, if I recall correctly, when I introduced Lie algebras last time, I don't think I spent time defining the algebra homomorphisms. So let's pretend that I did it last time, and then now we're recalling what they are. So if you have Lie algebras, mathfrak G and mathfrak H, then Lie algebra homomorphism is linear map phi going from G to H such that phi of the bracket of X and Y is the bracket of phi X, phi Y. So for any X, Y in G. So in other words, a Lie algebra homomorphism is, as you expect, it preserves things that we associate that are included in the definition of a Lie algebra. And what is in the definition of Lie algebra? Well, it's a linear structure, right? So it needs to be a linear map to preserve the linear structure, and then it needs to preserve the Lie brackets in the following way. So that is what a Lie bracket homomorphism is. And what then this previous result says that if you have a group homomorphism between two matrix Lie groups, then at least as far as the matrices coming from the exponential maps are concerned, they are completely determined by a map of the vector spaces. So a linear map of vector spaces given by this here, which determines what this thing will do. And this makes a lot of things a lot easier because it's a lot easier to check. So there are not that many linear maps of vector spaces. And there are certainly and even fewer that preserve the Lie brackets. So that reduces the space a lot when trying to consider these what kind of group homomorphisms there exist between two groups. So let's do the proof, and then I think that will be all for today. So the way we define, so what we will do, let's call this one I and this one I, and then let's say is that we start by defining. Okay, now this is not really correct. So let's do it like this. So if X is in G, then gamma of T equal to phi of ETX is a group homomorphism from R to H, which means there is some set in the Lie algebra of H such that gamma of T is equal to ET set. So because I can combine a group homomorphism into the Lie group of G with a group homomorphism taking me from G to H, I now have a group homomorphism into H. All such group homomorphisms from the real numbers into H has to be the exponential of something, and that something is set. And I use that to define set is then phi of X from this notion. Then ddt gamma of T T equals to 0 is equal to set, which shows number 2. And now I just need to do, as before, I need to show that this is actually a linear map, and I need to show that it preserves the brackets. So we show that it's a linear map. So phi linear. The reason for this is that if I take phi of E of TST, and this is equal to gamma of or my previous gamma of ST, which then is E ST set, which means that phi of SX will then just be the same as S set. So that's linearly thin in the first case, and then for plus, we have that if I have E T of phi of X plus Y, well, that's phi, that's large equal to large phi of E of T X plus Y. And then I can show that this is this limit. Then I can use this limit again, which we've used many times now. So whenever we want a plus from this matrix multiplication, this is the limit we go to. And now we use that, okay, this is a group homomorphism. of M, but this I can write as lim M going to infinity of et phi x of M, because we just showed that it was invariant under scalar multiplication. To the power M, and the limit here is et then phi of x plus phi of y here. Sorry. So in other words, this sort of so using the same sort of trick, we show that it's invariant under scalar multiplication and it's invariant under plus, right? Or yeah, equivariant under these operations. So what we'll have to now show is that it's invariant under these Lie brackets as well, that it gives us a group invariant. And I think I'll just release a separate video on that later this week. And I'll stop holding you. So then the next time I'll see you in person in Bergen, and we can continue with talking more about Lie algebras and Lie groups.